quick look, I would probably say, well, maybe my melting is about that much. Okay? And a lot of people would probably agree with me. And you go to do your integration, you hit accept. Now you have your enthalpy is about 37 joules per gram. Okay? However, there is something right there. It's very shallow, but it is actually there. And in fact, if we zoom in on that baseline, you can see that sort of drop off right there. Now that drop off is not insignificant. And I'll show you why here. So if I were to measure this entire thing as my melting, look at what happens. Now I go from an enthalpy of 37 to an enthalpy of 43. Okay? And it's just this little sliver of extra area that accounted for that. Okay? Now this is not a small change, clearly. What this is down here, because we did all this crystallization up here, okay? Crystals, and especially when it comes to polymers, crystals come or they form and they have different sizes. So not all the crystals are the same size. And so therefore within your melting transition you have a distribution of crystal sizes. Typically, when you see things like this, you definitely want to ask yourself what part of this is attributed to the melting curve and what part might be something different. In this case, this is actually part of your melting curve. And what happens if you look at certain equations in thermodynamics, you would see that as your crystals get smaller, the melting transition also gets small. So the temperature at which you melt the crystals is lower for smaller crystals. So essentially this sliver here that we first left out are those smaller crystals that were formed as it was crystallizing, and now it has to be included as part of your full melting curve. So I did this just to show you that things like this can definitely happen, and you want to sort of ask yourself those types of questions to make sure that you're doing the correct analysis and not leaving anything out. Okay?
Why the first cycle and the third cycle? Why
Yeah. Well, the enthalpies are different because
43 here, right?
this is 43 here.
First one.
Let's see if I measure this. You can see that the enthalpy here is 41.
How about the first one? The first
Right?
heat.
But the first heating, they were about 36 and 37.
Yeah.
Okay? Now remember, this first heating is dependent on what the original sample looked like.
Yes.
Right? Now that I got to 300, I no longer have that original sample. Right? Remember that first heat erases your thermal history.
Oh, okay.
So now whatever this shouldn't happen again.
Oh, okay.
Okay? Now my cooling scan, that is going to determine what I then see in my second heating. So that's why I measured this one really quickly, because you can see that this enthalpy is now 41, which is closer to the 43 that I just measured. Okay? So you can see that the cooling scan imparted its own history to the material that you can then read back in the subsequent heating. Right? So that's why it looks different, and that's why the numbers are different. Right? Because you're imparting something completely different than the original material came in.
So that means the first heating cycle is not
It depends on what you're there to measure. If you wanted to measure your first heating, if you cared about what the material originally looked like, then your first heating is important. Right? Now, if you didn't care what your original material looked like, then this would be the important one. Your second heating would probably be the important one to you. Okay? And that's what I was explaining before in terms of like if you were synthesizing your sample, perhaps the first heat's going to look like this, but that's not necessarily the original material or the material in its equilibrium state, because this all happened because you were synthesizing your material and because you precipitated it and because you filtered it and did all these other things. Those impart thermal histories to your material. that can trap it in different configurations that it doesn't necessarily want to be in, right? So now when you go past your first heat, you erase all of that, you get your original material and it's sort of, it's more comfortable or more relaxed state, and then you can then analyze what might be happening to your material in sort of more natural form.
So, for example, this sample is polymer. Mm-hmm. In your opinion, then what's the TC should be confirmed by the cooling?
Yeah, the TC will then be confirmed by the cooling scan and not by the heating scan.
And then the melting point.
Then the melting point would then be here.
Okay.
Yeah.
How about the TG?
The TG would be this. Yes.
Okay.
If you don't care about, again, if you don't care about what happened to your sample originally, then this is your TG. Yeah.
Okay.
All right. This is your bulk TG as it's defined. Okay. So again, you have to be mindful as what's important to you. Yeah. It's not about which one's more important. It's what's important to your study. Okay. Because not everybody's going to necessarily care about the first heat. Not everybody's going to care about the second heat.
Okay.
You have to understand which one is more applicable to the study that you are trying to carry out. Okay. So that's basically how you would analyze in a simple way this material, and you can see, like I've shown, that different things can happen in different locations, and you have to be mindful of what they are, what they mean with respect to the study that you're trying to carry out. Now I'm done doing all the analysis and all that stuff. I want to save all this because this is, this could be a lot of work. One thing that's really nice is that you can actually right-click and simply copy these. You can copy and paste these graphs directly on a PowerPoint. If you have, a group meeting or some very quick presentation, you can simply copy everything on there. If you want a more, a better saving method, if you go all the way up to the top left and this trios icon, you click on that. You can hit Save As and save it to a PDF. So the PDF will save whatever is on the screen, essentially. Okay? And if I go, I'm just going to save it to the desktop for now. And what you would see if I go to my desktop, this is my PDF. So the PDF basically contains all of the things I just analyzed. The title, all the X and Y axes, my convention of exothermic up. Everything is added to the PDF. So you can basically, save that and take that with you. If you want the raw data, for example, if you don't have trios as yet, you go to the actual file, you right-click, you say export, and you can either export it as a text or Excel. Most people would probably prefer Excel. So you click on that, and in the Excel sort of menu here, you can actually select or deselect which steps you actually care about, right? So in this case, I want all of the data, so I want all 3 steps. The last step is typically empty, so you don't have to copy that. But you select which ones you want, you hit OK. It will basically build the Excel spreadsheet. It'll say that the file export is successful. And if I go into where it just saved it, you can see it saves it directly wherever your file is saved. So if this was saved in your folder, it'll pop up right into your folder. But essentially, when you open the spreadsheet, you will see that you'll have 3 default columns: time, temperature, and heat flow, normalized. And each one of the tabs is a different step in your experiment. So the first page is actually details, which is, all the things that you typed into that sample information is basically all going to be here. Then the other page is going to be your first set of data. So this is your first heat, then your first cool, and then your second heat. Okay, so they're all going to be split up into different pages that you can build and analyze separately. Now let's say these again are default. Let's say that I want to add another column with some different type of data. Let's say I wanted to add my heat capacity. All I really need to do is plot the heat capacity on this plot. So if I right click, go to select variables, and let's say I plot my heat capacity on my second y-axis over here, and I hit OK. So now I have the second plot. All I have to do now is resave the data. File export successful. And when I go in, I have another data file. And you can see now I have my heat capacity column plotted right up there. So I don't need to necessarily manually do any calculations in here. As long as I can plot it on that graph, I can save it as its own data set and have a separate column with it right there. So I don't need to do any extra stuff going into any other software or anything like that. Everything can be done directly through Trios and then basically just copied out. Okay, which I think is actually pretty nice. So once you have your raw data, you can basically go ahead and do whatever you want with it. You can plot it on your favorite plotting software and things like that. The only thing I would not suggest is I would suggest not trying to do this on other types of software or other more generic types of software, I should say, simply because the units and the way that it would integrate these things, I don't quite know how it would do that. Typically what they do is fit things to Gaussian curves and things like that. And if you know about Gaussian curves, the area under the curve of a Gaussian has no units. So the numbers that will come out would make no sense. In this program, it knows what these curves are. It knows what the units are. So everything comes out in the correct units with the correct numbers. So I would strongly suggest doing all of your analysis here or on Trios, and doing it exactly like I did it here. Just have all the numbers in front of you. You can save this. You can save the file just that this will open up exactly as is. You can save the PDF, whatever your favorite way is. And then you can take your raw data and replot it somewhere else and simply just add these on afterwards. If you try to do these analyses in other sort of more generic software, it simply just won't really work, or it would require a lot of your work to make it make sense. So it's just much easier to do it through this. And like I said, this software is free, so there's really no cost to just doing it here. Okay. Yeah, so that's basically how you analyze a relatively simple material. Of course, not all of your materials are going to look exactly like this. Some of your glass transitions are going to look a little weird, and your melting is going to have maybe more than one peak, and all these things have specific meanings to them. Just be careful of how you analyze them and how you interpret what those things are. But this is sort of a general direction in terms of doing your proper analysis of a DSC sample. Okay. So that's basically it. The last thing that we would do is that I would show you how to physically prepare a sample, and the two numbers that you would need to put in up here, where you would get them from. All right. You can pause it for a second. You can pause it. Yeah.